good. This one.
Problem. Okay.
That
Thank you again. I again apologize for this inconvenience. Hello again. I'm excited to share our recent work on the non-local interference in arrival time. In fact, this is a new approach to analyzing the entangled systems. I hope you will find my talk interesting and informative. I also want to acknowledge my colleague, Dr. Kazemi, who gave a great talk before me. In his lecture, we saw that we can still use the double-slit experiment for a deeper understanding of quantum physics. And this experiment can distinguish between quantum interpretations. No wonder that Feynman said that the double-slit experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery. Yet, if there is an experiment more mysterious, it is a double-slit experiment with entangled particle pairs, because in this experiment, the two most important properties of quantum theory, namely superposition and entanglement, combine and lead to a non-local interference pattern. The full analysis of the two double-slit experiments can be even more complex, because the third quantum effect, that is the collapse of the wave function when the first particle is detected in the middle of experiment at random times. This problem becomes more complicated in the standard quantum mechanics, when the particles are entangled and there is an external potential. As we can see, when the right particle arrives at the right screen, the left particle is still en route to the left screen. This can change the detection statistics. However, we see that the one particle patterns don't change through this effect, and the no communication theorem is still holds. Although this picture is deterministic, and we know that such a picture does not exist in the standard quantum, the problem still persists, because before the detection of the first particle, the evolution of the wave function, in fact, the evolution of the wave function is a two-particle wave function. And when the first particle is detected at t equal to tc, that is the collapse time of first particle, the whole wave function collapses, and this collapse changes the dynamic of the whole system, which includes the second particle. As you know, since there is no unambiguous prediction for the arrival time of the particle in the orthodox quantum, especially for entangled state and in the presence of external potential like gravity, we cannot have a clear prediction for the joint two-particle arrival time distribution in the standard approach. In fact, this is a practical encounter with the measurement problem. To overcome this problem, we use Bohmian mechanics, that is a version of quantum theory that avoids the measurement problem and can lead to a clear prediction for arrival time distribution using the Bohmian trajectories. As we see, after the detection of the first particle, the dynamic of the left-hand particle is governed by the guidance equation for a single particle. As you know, we have just a conditional one-particle wave function that is explicitly dependent on the first particle arrival position and implicitly on its arrival time. Consequently, we see that the arrival time and position of the left particle are changed. By simulating the trajectories of the particles for the true double-slit experiment with vertical screen and without the presence of an external potential, we observe a true particle interference in the arrival position distribution. As you can see, the green trajectories in the left figure are simulated without considering the first particle collapse effect. And the black trajectories are simulated by taking this effect into account. The scatter plots on the right side show the spatial distribution of particles arriving to the left and right screens. In this plot, we assume that the left screen is located at a distance of 1 centimeter from the two left slits, and the right screen is located at a distance of 50 centimeters from the two right slits. The vertical axis corresponds to the arrival positions on the left particle and the horizontal axis correspond to the detection position of right particles. And obviously the green plot is for the case where you do not take the collapse effect into account, and the black one is the correct distribution collapse effect. For this setup, we can also calculate the joint distribution of arrival time of two particles. But as you see, we do not have any interference in this distribution. However, with some simple modification to the setup, such as using horizontal screens instead of the vertical ones, and applying an external force, such as like gravity, it becomes possible to create interference between the wave packets in the direction of the propagation. This opens up the possibility of observing interference in the arrival time joint distribution. The presence of a gravitational field adds excitement to the problem, since entangled particles fall free, allowing for testing of the equivalence principle in entangled systems. For numerical simulation, we have used the wave function in this form. The first term, which we call cross mode, is related to the maximally anticorrelated state, and the second term, which we call parallel mode, is related to the maximally correlated state. We can control the degree of entanglement with the eta parameter. So when eta is -1, the system is maximally anticorrelated. As you can see in this picture, when a particle on one side passes through the upper slit, the other particle on the opposite side passes through the lower slit, and vice versa. When eta is equal to 1, the system is maximally correlated, and the particle will both pass through the upper slits or the lower slits. As eta approaches 0, the intensity of entanglement decreases, and when eta is equal to 0, the two particles are completely unentangled. We define this term using Gaussian functions and symmetrization for bosonic system, where G is obtained by multiplying Gaussian function in each dimension. If we put the solution of Schrödinger equation in the presence of the gravitational field in this equation, the time-dependent wave function is obtained. This form, in fact, this form of initial wave function is commonly used in the literature. As you can see in this picture, some of Bohmian trajectories are plotted for maximally anticorrelated helium atom pairs. In this figure, the cyan trajectories are plotted without considering the collapse effect, and the black ones are with it. We can see that some of black trajectories are start deviate from the cyan ones as the screens detect the counterpart particles, and the conditional wave function now guides undetected particles. It is worth noting that the ensemble of trajectories can be experimentally reconstructed using weak measurement techniques, which can be used as a test of this result. By calculating the joint arrival time distribution of entangled pair of particles whose initial position are randomly generated by the initial wave function, we observe an interference in the two particle arrival times that has not been predicted or observed so far. As you see, the joint arrival time distribution and marginal arrival distributions of right screen are plotted for sodium atom pairs for different entanglement levels, which are controlled by eta parameter. In the dark cyan plots, the collapse effect is ignored, and in the black plots, this effect is considered. In this figure, we see the one particle and two particle temporal interference pattern for fixed screen locations. As we can see, the visibility of the joint and marginal distributions have an inverse relation. When the one particle interference visibility is maximal, the two particle interference visibility is minimal, and vice versa. This behavior represents a temporal complementarity between the one particle and two particle interference visibility of arrival time pattern. We numerically study this complementary relation for arrival time interference pattern. In this regard, the visibility of arrival time interference pattern for the case represented in the previous slide are shown in this figure. The one particle visibility is shown with blue squares, the two particle visibility is shown with black diamonds, and the sum of their squares is shown with gray circles. As you can see, the one particle and two particle visibilities have opposite behavior, and the sum of their squares satisfy the mentioned complementary relation. We have also calculated the entanglement entropy as a function of eta, which is a measure of the degree of quantum entanglement between two particles, and is given by the one particle density matrix. As we can see, this quantity has a very similar behavior with two particle interference visibility, which leads us to propose the two particle visibility as an entanglement witness. At this point, there are two important questions. The first question is how much the detector screen can change our results. There are two main approaches in this regard. Some believe that the detector as a microscopic system cannot affect the evolution of the wave function before measurement. And others believe that the effects of the detector should also be considered. The second question is how well the semi-classical approximation can reproduce these results. Since this approximation is used to calculate the arrival time in similar experiments such as ghost imaging, interferometric gravimetry, and atomic Congo-Mendel experiment, it is important to check how much our results deviate from this approximation and how much it can affect the analysis of these experiments. To answer the first question, we simulate the effects of the detector based on the absorbing boundary role model, which is compatible with Bohmian mechanics. If the sensitivity of the detector to the momentum of the particle significantly differs from the average momentum of arriving particles, they can be reflected from the screen several times. As we can see in the upper panels, the trajectory of the particles represents this reflection, and in the scatter plot of the two particle arrival time, we observe a repeating pattern which is like a fractal pattern. Please note that this figure shows trajectories only for right-hand side double slit. In the two double slit setup, that is with maximally entangled helium atoms and screens placed at the same height. By choosing the proper sensitivity for the detector, its effect is almost insignificant. This is evident in the bottom panel. These trajectories are simulated without, in the right-hand side. These trajectories are simulated without considering the effect of the screen, and these trajectories are with the absorbing screen whose sensitivity is chosen correctly. We can see also that the scatter plots of these two is very similar. Panel G corresponds to trajectories in panel C, and panel H corresponds to the trajectories of panel D. We observe the same interference pattern as in our previous calculation. This confirms the validity of our previous calculations. To answer the second question about the validity of the semi-classical approximation, we compared the results obtained by the Bohmian method with the semi-classical approximation for two different screen distances. This scatter plot are the two particle joint arrival time distributions based on the Bohmian approach when two screens are located at same level. This plot on the left-hand side shows the screen that the screens are placed half a millimeter below the slits, while in this one, the screens are located 1 centimeter away from the center of the two slits and below them. There are various ways to calculate the distribution of arrival time using the semi-classical approximation. All you need to do is to consider the initial position and momentum joint distribution of the particles, and then use classical method to calculate the arrival time during free fall. This can be done using this classical formula. However, it's important to remember that the uncertainty principle prevents the existence of a combined distribution for both particle position and momentum. This is why the semi-classical approximation can produce multiple predictions. If we use the raw semi-classical approximation, the initial distribution of position and momentum are independent, and we can write the joint distribution in this product form. Also, the initial position of all particles is assumed to be in the center of each two slits. In this case, the shape of the distribution does not change significantly for near and far distances of the screen. And we see a big difference between the results of this approximation and the result of Bohmian simulation for near distance of the screen. Another way to consider the initial distribution of position and momentum as the result of multiplying the wave functions squared with the square of Fourier transform. In this case, for near distance, we can see that this distribution is more similar to the Bohmian distribution compared to the previous semi-classical distribution. However, when looking at the far distance screen case, it is entirely distinct from Bohmian distribution. As you can see, the central fringe is removed in this plot. Another option is that the initial distribution is not in the product form. In cases where the initial distribution is not multiplicative, we observe an increase in the difference with the Bohmian distribution. Even in marginal distribution, we see that the semi-classical approximation leads to different results. In fact, this indicates that the semi-classical approximation is very sensitive to the initial conditions in the setup. And so this experiment can be used to test Bohmian arrival time distribution in a strict manner, that is where the semi-classical approximation is broken down. Especially since these results are obtained in the far field regime and in the absence of backflow effect, its experimental realization is possible thanks to the current present-day single-atom interferometry technologies. We hope that this experiment will be carried out as soon as possible and enrich our knowledge of quantum foundations. Thank you for your attention and participation.
Yes, do we have any questions? So I have a question. It kind of applies to both your talk and Mohammed Jawad's, which wasn't really clear to me. That you talk about these different kinds of detectors when you're modeling, different ways of modeling the detector back action, right? But do you have any idea what those different choices would actually correspond to physically if I wanted to try and build a detector in an optimal way?
Thank you for your question, Mark. If I understand correctly your question, this is about the detector back effect in two or words. In fact, in the previous talk, or in previous work, we also simulate this detector back effect that is absorbing boundary rule, and I present this in my talk here. There are various models and methods for simulating the detector. And if we can simulate all of them, I think that there is no agreement on the results of these methods. And actually, we have a strict need to have a comprehensive attention to these effects, to have more understanding of effects of the detector to the wave function evolution before the particle detection.
I see. Okay, so more work to be done. Thanks.
Thank you very much.
So let's thank Ali again.